Lecture 7 of Modeling and Simulation of Physical System, in which we shall continue our discussion on the systems containing both translational and rotational elements using Lagrange's method. With the help of more examples, I hope to further illustrate the application of Lagrange's method for the two-link manipulator, mass pulley system, electrical motor with a load, as well as the example of rolling wheel with a spring that we solved using the basic principles and techniques for modeling the systems with both the translational and rotational elements. A two-link planar manipulator contains two rigid links L1 and L2 connected with the help of a joint A as shown here. So one end of link 1 is connected to link 2 at joint A. The other end is representing joint 0, which provides a pivot, and link 1 is going to rotate about this pivot. The joints are modeled as rigid links, and therefore as they rotate they are going to exhibit rotational kinetic energies. The joints, on the other hand, in reality are actuated by some actuator such as electrical motor. However, in this case, our model does not include the dynamics of an electrical motor. Therefore, these joints can be considered as ordinary joints which offer connectivity between the links as well as some friction at the point of contact. And the friction is modeled by means of a rotational damper because there is a rotational motion about these joints. So the damping coefficient of a rotational damper representing friction at joint 0 is B1. The damping coefficient of joint 2 of joint A damper will be B2. In order for this planar manipulator to perform some useful task, the other end of link 2 is connected to what we call as the end effector. In this case, the end effector is shown to have a gripper-like shape through which it can perform some useful task such as pick and place that is very common in industrial application and settings. The link 1 makes an angle θ1 with respect to x-axis, and link 2 makes an angle θ2 with respect to the axis represented by dotted line that is drawn along the length of link 1. In our model of a two-link manipulator, the link 1 mass moment of inertia will be taken as J1, and the link 2 mass moment of inertia is taken as J2. Now note that in case of link 1, we can only expect to have a rotational motion which corresponds to the displacement variable θ1. However, in case of link 2, it is going to exhibit two types of motion, one of them being the rotational motion about joint A. However, there is another type of motion that will be the translational motion due to the fact that the joint A is not fixed and it can move as the link 1 rotates. Therefore, the axis of rotation of link 2 is not stationary, and because of that, link 2 shall also exhibit some translational motion. For that, we need to specify the center of gravity of link 2. It is shown here, CG, taken somewhere in the middle. So the center of gravity of link 2 is marked CG. The problem asks us to write down the expression of total kinetic energy, potential energy, and the dissipation energies of this two-link manipulator. And once we have those expressions, we can write down the Lagrange's equation to write down the equations of motion. But first of all, we have to explicitly write down the model assumptions. We are going to assume that there is no force responsible for the gravitational pull on the links. Therefore, the gravity is not going to be modeled. Then we need to define the reference axis system, which in this case is fairly straightforward. We have an x-axis and we have y-axis. Furthermore, as already assumed, the links are modeled as rigid bodies and they have corresponding mass moment of inertias and masses. We shall also assume that the end effector has negligible mass. Therefore, it is discounted from the system dynamics. And finally, the joint friction has been modeled by means of a rotational damper. The corresponding damping coefficients are taken as B1 and B2. And last but not least, we shall assume that the angular velocities of both the joints, at both the joints, meaning the angular velocities of link 1 and link 2 are both finite. This condition is required to avoid the singularity situation, of which you will learn more details in your next semester course on robotics. The most complicated part of this problem is to write down the expression of the total kinetic energy of the system. It is a sum of total rotational kinetic energy TR and the total translational kinetic energy of the system. The total kinetic energy of the system can be easily attributed to the kinetic energies of the two links L1 and L2. Let us do the easier part first, that is, writing the expression of rotational kinetic energies of both the links. As we know that link 1 makes an angle θ1 with respect to x-axis. Therefore, converting that angular displacement into angular velocity should give us θ1 dot. So half time J1 θ1 dot square becomes the rotational kinetic energy of link 1. What about the rotational kinetic energy of link 2? Again, we have to be consistent as far as the displacement variable of link 2 is concerned. Remember, the displacement variable of link 1 was θ1, that was with reference to the x-axis. So we need to have a displacement variable for link 2 with respect to the same axis, x-axis. In this case, we know that link 2 makes an angle θ1 with respect to link 1, and then link 1, this really should have been θ2, and then link 1 makes an angle θ1 with respect to x-axis. And these two angles add up to give the total angular displacement of link 2 with respect to the x-axis. Again, this highlights the importance of first defining the reference axis system before writing the expressions of kinetic energy, potential energy, or dissipation energies. Therefore, the total angular displacement, hence the total angular velocity of link 2 will be θ2 dot plus θ1 dot whole square times the mass moment of inertia of link 2 divided by 2. Combining the two rotational kinetic energies should give us the expression shown here. Next, we proceed to the expression of the translational kinetic energy of the system. As described earlier, link 1 has no translational kinetic energy because it is rotating about a pivot shown by joint 0, and the only motion link 1 exhibits is that of the rotational motion. However, link 2 is joined to link 1 at joint A, and this point about which the link 2 is rotating is not stationary. In fact, it moves as link 1 moves. By virtue of the non-stationarity of joint A, link 2, in addition to the rotational motion, also possesses a component of translational motion. Therefore, when it comes to writing the expression of translational kinetic energy of the system, we shall only refer to the translational dynamics of link 2. And for that purpose, we need to first compute the linear velocity of link 2, and that needs to be calculated at the link 2 center of gravity, CG. In order to formally calculate the translational kinetic energy of link 2, it is important to define a position vector for the center of gravity of link 2. Call that dCg, or d subscript Cg. Note that the straight line distance between the tip of link 1, that is from joint A to the center of gravity, is c. Now we are not going to directly manipulate this position vector defining the position of the center of gravity of link 2. In fact, we shall write down the x component of this vector as well as the y component, and then manipulate the two separately. So let us calculate the x component of this position vector. Project dCg onto the x-axis of the system. We find that the x component of this position vector is a sum of L1 cosine theta 1 plus and c cosine theta 1 plus theta 2 by doing some simple geometric calculations as well as trigonometric calculations. So xCg is L1 cosine theta 1 plus c times cosine theta 1 plus theta 2. And it is because that this point over here, the center of gravity, this vector dCg can be thought of as a sum of this vector OA plus ACG. And what we have done here is that we have added the x component of vector OA, which is L cosine theta 1, plus c cosine theta 1 plus theta 2, which is the x component of vector ACG. This is c cosine theta 1 plus theta 2. Likewise, write down the y component of dCg. So yCg is the y component, and again we look at this vector dCg and we wish to compute the length of this vertical line, which is simply a sum of L1 sine theta 1 plus c times sine theta 1 plus theta 2. Now, in order for us to be able to utilize the position variable xg, xcg and ycg for the calculation of kinetic energy, we first need to calculate their respective derivatives so that we can talk about the velocity of link 2 at its center of gravity, that is the linear velocity, which has two components, the component along x-axis and a component along y-axis. For those velocities, take time derivative of xcg and ycg. And because xcg and ycg, they are both function of theta 1 and theta 2, it is important to remember that both the displacement variables are function of time. Therefore, the calculation of corresponding velocity variable requires application of chain rule. Therefore, when we take the time derivative of xcg, apply chain rule to get minus L1 sine theta 1 multiplied by theta 1 dot minus c sine theta 1 plus theta 2 multiplied by theta 1 dot plus theta 2 dot. Then square the velocity, that is xcg dot square, and you will arrive at this elaborated expression containing several terms, some of them involving the product of multiple sinusoids such as sine theta 1 plus theta 2 multiplied by sine theta 1. And then you see the terms containing squares of the displacement variable, the second order angular displacement. In fact, these are the sum of the product of angular velocities. Likewise, calculate ycg dot to obtain the expression, and squaring that will give us a corresponding expression containing several terms. Some of them are the product of cosine, such as cosine theta 1 times cosine theta 1 plus theta 2, and again that will be multiplied by the sum of the product of the angular velocities. However, a simplification occurs when we plug in the two terms in the corresponding kinetic energy. So remember, xcg dot square represents the kinetic energy of link 2, that is the translational kinetic energy of link 2 along x-axis, which is this term, and the kinetic energy of link 2 along y-axis is this term, that the one that contains ycg dot square. The mass and the center of gravity of link 2 is the same in both cases, that is m2. And if we plug in the expression of corresponding linear velocities, the final expression is somewhat more simplified due to the fact that some of these terms are simplified, noting that sine square theta plus cosine square theta equals to 1. And moreover, the last two terms can be combined to give us cosine theta 2 minus theta 1 minus theta 2, which is cosine minus theta 2, same as cosine theta 2. This will be the expression of total translational kinetic energy of the system, and once again we emphasize that that is totally attributed to the translational kinetic energy of link 2. There is no translational kinetic energy associated with link 1 that only exhibits rotational kinetic energy. Hence, we have almost completed our job. The expression of total translational kinetic energy is shown here, and the total rotational kinetic energy of the system has already been calculated. When the two energies are added up, we can write down the expression for the total kinetic energy of the system. You can match this expression with the one given in the textbook, although the expression has been obtained by a somewhat different approach. That might be worth learning as well. There is no potential energy in the system, no rotational or translational motion associated with the springs. and also due to the fact that we have ignored the gravitational pull. So the potential energy will be zero. However, there is some non-zero dissipation energy attributed to the frictional effect modeled by means of the rotational damping on both joints. That is simply half times B1 theta 1 dot square times half plus half times B2 theta 2 dot square. The next example contains a pulley lifting some mass ml by means of a rope that loops around the pulley. The rope is extensible, meaning that it has some flexibility, which is modeled as a translational spring of stiffness K1. The mass is supported on a spring and a damper whose other end is fixed. The stiffness of the spring supporting the mass ml is K2, and the damper has damping coefficient B. The mass of the pulley is mw, and remember that pulley is modeled as a wheel rotating about its fixed axis. The diameter of the pulley is d, therefore the radius of the pulley is d over 2. The inertia of a pulley is taken as mw over 2 times the radius square, which is d over 2 whole square. So there's a typo here. It really should have been mw divided by 2. That's because the pulley has been modeled as a cylindrical disc. So we have already spelled out the model assumption that the cable is flexible, hence modeled after the translational spring of stiffness K1. Another important assumption that the cable does not slip over the pulley. This is important because otherwise we just cannot relate what's given in the problem, which is the input displacement applied downward on the rope as shown here. This displacement just cannot be related with the upward displacement x of the mass ml, unless we assume that there is no slipping. That is, the cable does not slip over the pulley. In order to write down the equations of motion using Lagrange's method, we first need to describe a convenient axis system. In this case, it is fairly trivial. We can just simply say that there is some axis, call this one x-axis or y-axis, and the only displacement, the linear displacement, is x, describing the vertically upward, or the vertical displacement of mass ml. And along the same axis, the input displacement has been defined, although in the opposite direction. And the axis also passes through the center of gravity, or the point about which the pulley shall rotate. So having defined that axis, we next proceed to describe the displacement variable qi. And in this case, we are going to take a displacement variable as qi equals to x. It makes sense because whatever vertical displacement is exhibited by the mass, same is the displacement of the pulley, the linear displacement of the pulley. So consider the situation as shown here, that the end of the rope where the mass is connected has linear displacement x, shown vertically upward. Then this linear displacement maps to an angular displacement exhibited by the pulley, and this angular displacement when converted back into the linear displacement x, it forms shape of an arc, whose length, arc length, is still x. Same x displacement can be taken anywhere along the circumference of the pulley, as shown here. The corresponding loading needs to be defined as well, capital Q of small qi. Let that be some force. It has to be a force because the displacement variable chosen here is a linear displacement, x. Suppose there is some force applied to the other end of the pulley, F. So now we have defined the displacement variable and the corresponding loading function in the form of a force. Later we shall show that because there is no external force given in the problem, there is no external loading F the way we have assumed, so we are just going to simply put F equals to 0. So right now, remember that the displacement variable x is taken in the direction of force. X is a linear displacement, and the corresponding angular displacement is simply x over r, which is x divided by d over 2, or 2x divided by d. The corresponding velocity will then be the angular velocity, simply the time derivative of the angular displacement, 2 over d times x dot. So now we're ready to write down the expression of the total kinetic energy of the system. In this system, there are two components or two elements which exhibit mass and the moment of inertia. The first one being ml, which has purely translational kinetic energy in the vertical direction. So that will be half times ml x dot square. The other component of kinetic energy is due to the rotational motion of the pulley. And the pulley rotates about fixed axis. Therefore, this component will be half times the mass moment of inertia of the pulley that we have already written down, mw divided by 2 times the radius square, that is d over 2 whole square, times the angular velocity, which is 2x dot divided by d whole square. This gives a complete expression for the total kinetic energy of the system. Then comes the total potential energy of the system. We can see that there are two springs with corresponding stiffnesses K1 and K2 in the system. The spring K1 has angular displacement u of d, which is essentially the input to the system. The other end of the spring, as we saw in the last slide, was displaced by an amount x. Hence, the potential energy stored in spring with stiffness K1 is half times K1 x minus ut square. Likewise, the potential energy stored in the other spring with the stiffness K2, whose one end is fixed and the other end has displacement x in the vertically upward direction. So half times K2 x square. Therefore, once we have calculated the potential energy, we can now proceed to writing the expression of the dissipation energy, half times bx dot square, where b is the damping coefficient. There is just one damper in the system, and there is no other source of damping of the friction that is included in the model. Hence, half time b times x dot square. In order to apply Lagrange, we need to calculate the partial derivatives of energies with respect to the displacement variable, which is x. So partial u over partial x is k2 times x plus k1 x minus u of t. Partial r over partial x dot is b times x dot, and partial t over partial x is 0. And that's because kinetic energy does not contain any term that involves x. In other words, it is not a function of displacement. However, it is a function of velocity x dot. So taking partial derivative of t with respect to x dot gives us ml plus mw divided by 2 whole multiplied by x dot. And finally, we need to calculate the time derivative of the partial derivative of kinetic energy with respect to partial x dot gives us ml plus mw divided by 2 times whole multiplied by x double dot. And once we have computed these partial derivatives and other terms, we can write down the Lagrange equation of motion. It turns out to be ml plus mw divided by 2, so here it really should have been 2, times x double dot plus bx dot plus k2x plus k1x minus k1u of t equals to f. Remember, there is no external loading in the form of a force F. Therefore, we must set F equals to 0. Once we set F equals to 0, then the final equation of motion that relates the input displacement u of t with the displacement of the mass can be found as shown here. Our next example is that of an electric motor rotating some load. The model of electric motor contains a disc representing the rotor whose angular displacement is taken as θ1 in the anticlockwise direction. The rotor is experiencing some torque, capital T, which is in the same direction as that of θ1. This torque is produced due to the interaction between the rotor and the stator magnetic fields. Note that in this problem, we are not going to explicitly model the electrical component of the electric motor. That includes the inductance and the resistance of the electric motor circuit. The rotor is connected to the load by means of a flexible shaft. The other end of the shaft is connected to a disc-like load whose mass moment of inertia is taken as J2. As the rotor rotates in the anticlockwise direction, it imparts an anticlockwise rotation in the load as well. However, load experiences an opposing torque, TL, often referred to as the disturbance torque. In its simplified model, the electric motor and the load system remains essentially the same. So this bottom diagram is essentially the same as shown in the top diagram, except that the shaft has been replaced by a torsion spring with the spring constant KT. And we have altered the notation for the torques. So it is a rightward torque, which is in the same direction as θ1, and the leftward torque, the disturbance torque TL, which is opposite to θ2. Note that θ2 and θ1 are in the same direction. To solve this problem, by that we mean writing the equations of motion, we first need to define a convenient axis. We know that both the rotor as well as the load, they rotate about the same axis that can be taken as simply the x-axis. We don't need to define any other axis to write the equations of motion. Now we are ready to apply the Lagrange's method, and our next step is to define an appropriate displacement variable. In this case, we can easily note that there are two displacements, each associated with the corresponding mass moment of inertia J1 and J2, that of motor and the load. So let Q1 is theta 1 and the corresponding loading applied to a point on the rotor where the displacement is theta 1, the corresponding loading, capital Q, the function of Q1, is the torque. This is given as part of the problem. Let Q2 equals to theta 2, meaning that the other angular displacement that describes the configuration of the system is theta 2. This theta 2 is associated with J2 that experiences torque. However, note that the loading is opposite to Q2 in this case. Therefore, capital Q must be minus TL. This is very important. Note that when we define the displacement and loading pair, both should be in the same direction, or the loading should reinforce the displacement. In the second case, the loading is acting in the opposite direction to theta 2. In the first case, the loading is rotating the rotor in the same direction as that of its angular displacement variable, that is theta 1. So once the displacement and the loading variables or the function have been settled, let's proceed to writing the total kinetic energy expression. In this case, there is no translational motion. The entire kinetic energy of the system can be simply attributed to the rotational motion kinetic energy of each of the two mass moment of inertia, J1 and J2. So that's just half times J1 theta 1 dot square plus half times J2 theta 2 dot square. Then the total potential energy of the system is the energy stored in the torsion spring. The expression is half times KT whole multiplied by theta 2 minus theta 1 whole square. And again note that you can also take theta 1 minus theta 2 square without any consequence. The next step involves calculation or the partial derivative of the energies with respect to the displacement variables theta 1 and theta 2. So we calculate the partial derivative of kinetic energy with reference to theta 1 dot as well as with respect to theta 2 dot, and then calculate the time derivative of those partial derivatives. It's shown here. Likewise, calculate the partial derivatives of the potential energy with reference to theta 1 and theta 2 separately to obtain following expression. Finally, there is no dissipation in the system model, hence there is no dissipation energy. Therefore, R equals to 0 and its partial derivatives with reference to theta 1 dot and theta 2 dot are likewise equal to 0. Also, as occurred in many cases, the partial derivative of kinetic energy with respect to theta 1 and theta 2 is also equal to 0. That is, kinetic energy is not a function of angular displacement, it is only a function of angular velocities. Because in this case, the dynamics of the systems is described by two displacement variables, theta 1 and theta 2, we shall write down two equations of motion based upon the Lagrange's method. The first Lagrange equation obtains the partial derivatives with reference to theta 1 and theta 1 dot, the left hand side, and equates the left hand side with the right hand side containing the torque, capital T, applied to the rotor of the motor. So remember the displacement and the loading pair, the first of them being theta 1 with the torque. The first Lagrange equation should give us torque equals to J1 theta 1 double dot plus KT times theta 1 minus KT times theta 2. The second Lagrange equation computes left-hand side utilizing the derivative of θ2 and θ2 dot, and equates that expression to right-hand side where the loading is minus TL. So remember, minus has been used because TL is opposing θ2. After simplification, the expression of second equation of motion will be minus TL equals J2 θ2 double dot plus KT times θ2 minus KT times θ1. As a homework exercise, you are required to develop the state space model of the system using the two Lagrange's equation and put TL equals to 0. Our last example is a familiar one, that of a rolling wheel and the spring. We wrote equations of motion for this system 2 lectures ago when we studied the general techniques for writing the equations of motion for the rotational mechanical system. However, we said then that that was actually an example of a system containing both the translational and rotational elements. We are going to revisit this problem by trying to solve it with the help of another technique, that is the Lagrange's method. And so this time the equations of motion will be obtained from the Lagrange's method. In the problem setup, remember that there was a rolling spring that is attached to the spring whose stiffness is K. The spring is actually attached to the center of the wheel, O. The other end of the spring is rigid, it is fixed, therefore there is no displacement. However, the terminal of the spring attached to the center of the wheel has some linear displacement x. In its model, the wheel radius is taken as small r and its mass is small m. The model further assumes that, and the first assumption is very important, which is the wheel rolls without slipping. That is, there is no slipping of the wheel and it rolls without slipping. And a lot of things, and this assumption has some significant consequences, as we shall see in our further discussion. For that, the center of gravity needs to be specified for the wheel, that is O. And finally, there is some force, external force, that is applied to the top point of the wheel A, as shown here. Therefore, in order to write down the equations of motion for the system using Lagrange, we first need to define convenient axis. And obviously there is motion along one axis, and that can be just taken as x-axis of the system. But note that there are two types of motions, one of them being the translational motion indicated by the displacement variable x. There is, however, another type of motion, and that is the rotational motion of the wheel. And that is the reason why the wheel is rolling on the surface. In fact, the translational motion comes about due to the rotational motion of the wheel. Then, in order to write down the Lagrange's equations of motion, we have to specify the displacement variable and the corresponding loading function. So let the displacement variable be simply taken as Q1, and capital Q of Q1 in this case is taken as F, the force which is given, and that may not be equal to 0. So non-zero force is given as part of the problem. It defines the loading. But what about the displacement variable Q1? One of the important things to note and to learn from this example is that the loading function is taken at a point where the displacement variable is small q1. So in order to define what exactly is q1, we have to look at the type of displacement at point A. So this loading q, that is the force, is applied to point A of the wheel. So q1 must be some linear displacement because the corresponding loading is force, is a linear displacement at A where loading F is applied. To carefully understand the nature of q1, we consider a scenario where the wheel is rolling on the surface, and more specifically, when a wheel rolls, the center of the wheel, that is the center of gravity, point O, shifts from O to O prime. And the top point of the wheel A becomes A prime as shown here. So if we connect A with A prime with the help of a vector, this is how it looks like. It is not perfectly horizontal, it is slightly tilted downward. But what about the vector joining O and O prime? That is a perfect horizontal arrow, leftward arrow. And we know that the length of this arrow is x. We say that the distance between O and O prime is the displacement x, that is given as part of the problem, that the center of the wheel has been displaced by displacement x. But what about the displacement, the linear displacement of the top of the wheel? That is the distance between A and A prime. Now that is q1. Now if we understand the mechanism of a rolling wheel without slipping, it can be known that in a limit when x is a small value, a small displacement, or when x is taken as instantaneous displacement, then q1, that is the displacement at the top part of the wheel, is approximately twice the displacement at the center of the wheel. That's because the velocity is double or approximately double compared to the velocity at the center of the wheel. More specifically, we are talking about the linear velocity. And in this limit, the two displacements or the two velocity vectors, whatever we talk about, either velocity or displacement, they are parallel. Therefore, the linear displacement at point A is approximated as twice that of x due to the mechanism of a rolling wheel without slipping. So q1 is 2 times x. That is the correct displacement variable corresponding to the loading function f in this case. Once the correct displacement variable has been identified, that is q1 equals to 2x, that is when we talk about the instantaneous displacement at point A, then the rest of the task becomes very easy. We can easily write down the expression for the total kinetic energy of the system, which is sum of translational kinetic energy and rotational kinetic energy. The translational kinetic energy is due to the motion of the wheel along the displacement variable x. Therefore, in order to write down the expression of translational kinetic energy, as seen several times before, we need to know the mass of the wheel. And the center point of the wheel can be simply taken as the center of the mass of the wheel. So we can just say half times m, where m is the mass of the wheel, times the velocity square. The velocity is simply the derivative of displacement x. The other part of the kinetic energy is the rotational kinetic energy. That is due to the rotational motion of the wheel, and that rotation occurs about the center of the wheel O. Although, again, it is reminded that the center of the wheel is not fixed. It is following a linear motion along the direction of the displacement x. And that is why we are talking about the translational kinetic energy, and we have written down the expression. But the wheel also has rotational kinetic energy due to its rotation about the center, O. That is half times its mass moment of inertia, J naught, times theta dot square. And with theta is the angular displacement. And we know that theta, although the expression for that is not explicitly written, but theta is just the displacement x divided by the radius of the wheel. So that is going to be x divided by r. When the time derivative is taken, that becomes x dot divided by r whole squared. And J naught is the mass moment of inertia of a cylindrical disk. That is mr squared divided by 2. The total kinetic energy, the sum of translational and rotational kinetic energy, becomes 3 over 4 mx dot square. The system also has some potential energy due to the spring. That is simply half times the spring coefficient, the stiffness K, times the displacement square. There is no friction in the model, hence R equals to 0. And we are now ready to write down the equation of motion using Lagrange, in which the right hand side is a loading function f, which is in the same direction as that of q1, and the left hand side contains term of partial derivatives with respect to q1 or q1 dot. Because the left hand side of the Lagrange's equation contains partial derivatives of energies with respect to x and not q1, which is 2x. We need to be a bit careful about calculating the partial derivatives with respect to q1 or q1 dot. So for that, first note that q1 is twice of x. That means x is half of q1. Therefore, dx over dq1 is half. Likewise, the corresponding velocities x dot would be half times q1 dot. Therefore, the derivative of x dot with respect to q1 dot is also half. If we next proceed to calculating the partial derivative of kinetic energy with respect to q1 dot, apply chain rule to split this derivative into partial derivative of kinetic energy with respect to x dot times the derivative of x dot with respect to q1 dot. That turns out to be 3 or 4 times mx dot. And taking the time derivative of the resulting expression would simply give us 3 or 4 times x double dot times the mass. Likewise, if we want to calculate the partial derivative of potential energy with respect to q1, this partial derivative can be written as a product of partial derivative of potential energy with respect to x times the derivative of x with respect to q1. That turns out to be half times kx. The remaining two terms on the left hand side are both 0. That's because there is no dissipation energy in the system, and the kinetic energy is not a function of displacement variable, either x or q1. Putting the expression of putting the expressions of the partial derivatives of the energy give us the final equation of motion, that is 2 times F equals to 3 over 2 times mass of the wheel times x double derivative plus k times x. And this is the exact same result as given for the rolling wheel and the spring problem in the textbook in equation 3.100. However, in that example, the expression was derived from an entirely different technique that assumes friction, that models a frictional force between the wheel and the surface that prevents wheel from slipping. In either case, the expression, the final equation of motion remains the same. The other method was discussed thoroughly in lecture 5. So therefore, it will be worth referring to that example. The same problem, same example solved from a different technique, but the answer remains the same. So with that, I would like to conclude our lecture number 7. I hope you enjoyed listening to this lecture, and I'm sure you will have lots of questions. So we are going to meet online on Thursday 2 p.m. for our regular questions and answer session. So till then, stay safe and goodbye.